Today we're going to be looking at chapters 18 and 19. Chapter 18 is interstellar medium, and chapter 19 is star formation. So we'll begin with 18. If we're looking out towards the Milky Way, which we can see if we're, well, certainly if you live where I happen to live in the Chicago area, there's so much light pollution that you can't really see much of anything. But if you went out to an area that was far away from the city lights and you looked up, you'd be able to see the billions of stars that make up the galaxy that we reside in, the Milky Way. And if you actually looked towards the Milky Way, one of the things that you would observe is that there appear to be dark bands running through the Milky Way. Now, this is not actually empty space. It's not space that's devoid of stars, but these are actually regions that have interstellar matter, which could be anything from very, very small particles, dust particles, to small concentrations, very small concentrations of individual atoms, mostly hydrogen atoms, that happen to occupy that portion of space, or at least the space that would be in front of us from where we are all the way out to wherever there might be a star that is actually lurking behind, or a series of stars that's actually lurking behind all of that matter. So basically it's just being blocked out. The light from the stars is being blocked out by this interstellar medium. So as I said, it's mostly made of gas and dust. The stars, when they're actually visible, you do see some stars shining through this. So when they're actually visible, they appear to be red in color, and this is because the particles and the atoms that happen to be present in this, or the few molecules that are present, are actually scattering the shorter wavelengths of light. Blue wavelengths are being scattered, and what is actually transmitted to us in our direction would be the longer red wavelengths. Infrared penetrates over the dark areas as well, but the shorter IR wavelengths are also actually scattered out, so we're mostly seeing the longer IR wavelengths. Gas and dust is omnipresent everywhere in the universe. But within these particular areas, these dark areas, there's a very, very low concentration of gas. On average, interstellar space contains something on the order of 10 to the 6, that would be 1 million atoms per cubic meter of space. So that's just, if you imagine, and that can actually range from 10 to the 4th up to 10 to the 9th atoms per cubic meter. Now that's 1 to 6 orders of magnitude less matter than we can achieve on Earth with the best vacuum that we can possibly produce. Dust particles are even scarcer than these atoms are, and there's only 10 to the -6th particle per cubic meter. That translates to about 1,000 particles per cubic kilometer, if you can imagine that. When you realize that in these nebular regions where we have this very, very black areas, the only reason that actually can block out light, when you realize that there's so little matter, is that there are so many meters of distance between us and whatever it is that we're looking at, that that in the aggregate of all those, even though it's only a very, very few atoms in that particular space, when you multiply that by the vast number of meters, linear meters between us and the light source, that actually becomes very significant, and it's actually enough to occult the light, to actually block the light out. When we talk about dust, though, I said that there's not a lot of dust in space, but Earth's atmosphere is actually even cleaner of dust than the rest of the universe, because we only have about 1 dust particle per 10 to the 18th. That would be a quintillion, 1 out of a quintillion atoms. For every quintillion atoms, that is, there would be 1 dust particle. So it's basically a millionth of what you would see in interstellar space. Particles are small. They're on the order of 100 nanometers in size, and nevertheless, even though they're very small, they're still large enough that they can block electromagnetic radiation. They can actually block light. Dust particles are elongated, and one of the reasons that we realize that there's kind of an axis to a dust particle, and the particles themselves actually seem to align themselves, all these particles align themselves in a particular direction. And one of the reasons that we know this is because if we actually examine light that is emanating from a distant star that is passing through a dust cloud like this, one of the things that we notice is that the light is actually polarized. Now what that means, that when light propagates towards you, so let's say we have a beam of light that's actually coming out of the board. It's, you remember that electromagnetic radiation is vibrating. So if it's coming out of the plane of the board, and we could actually look at it, we would see that it's, if this is the source of the light, it's vibrating up and down. But it's doing this in every conceivable direction. It's going this way, and it's vibrating that way, and it's vibrating this way, and there's really an infinite number of these vibrations occurring, in every direction. And it's, and it's not, since light doesn't really just propagate as a beam, this is actually going out through a sphere, so it's going in every imaginable direction. But just showing you one section of this sphere, the light is vibrating in all these different planes. Well, what happens is when light interacts with matter, it's possible for it to become plane polarized, where you'll get absorption in everything except maybe one particular plane. Now you can see that, for instance, if you use something like Polaroid glasses or a piece of polarizing film. If you put light through a piece of polarizing film, which will only allow transmission through one particular axis, it's kind of like having a gate. Everything that's not going, let's say, up and down, or if the axis of transmission is horizontal, everything that's not going this way is going to be blocked out. And the only light that we're going to see will be plane polarized. So if you've got a bunch of particles, and they're all oriented in the same direction, and that orientation could actually have to do, of course they're not close like this, because we said there are very, very few of these particles, but they all seem to align themselves in some way, probably because it's believed that there's probably a weak magnetic field that exists throughout space that's causing this kind of an alignment to occur. But if the particles are all aligned in one particular direction, then light will interact with every particle in the same way, so the light winds up being plane polarized. So that explains how that happens. If you cross two Polaroid filters, you've got one that's only transmitting this way and one transmitting that way, you'll get no light at all. The light will be completely cut out. So the light is plane polarized, and that, as I say, is an indication of the alignment of these particles. There are large fuzzy patches of light that are visible in some areas of the sky. And one example of this is the middle star, and the word star should be put into quotation marks because it's not really a star, but what we would actually look at as the star in the belt of Orion. Not in the belt of Orion, but in the, so if we look at, we've got stars, we've got Mintaka, and, you've got the other, you've got the star, Rigel and Betelgeuse, you've got all these stars here like that. And then there's a couple stars, there's like about 3 what look like stars down here that are actually forming, not the belt, but the sword. The middle one of these is actually what we call an emission nebula, and it's designated M42. And this designation is from the Messier catalog. Charles Messier, the French astronomer who I think was probably maybe 18th century, and he was the one that actually cataloged a number of these objects that weren't stars. Some of them are actually galaxies. Some of them, like this particular one, is something called an emission nebula. And so this is M42 is also referred to as the Great Orion Nebula, and as I said, is located within Orion's sword. What's causing the emission from this cloud of gas is ionization from ultraviolet radiation that's emanating from nearby hot stars. As the electrons and protons recombine to form hydrogen atoms, the red you actually get a red emission occurring. So again, you realize that what's happening here is that you've got electrons. You know that electrons are being excited to a higher energy level. We already saw this before several lectures ago when we were talking about the hydrogen alpha emission band, and we saw that when electrons fell from the second excited state to the first excited state, that when that actually happened, there was an emission in the red region of the spectrum, and we call that the hydrogen alpha line. That line occurs at 653.6 nanometers. And so we get red emission lines, and because of this, if we actually look at these nebular regions, they appear to be glowing red. So as the light reaches us, some of the starlight passing through the emission nebula may be scattered by nearby dust clouds, which can produce a secondary nebula that's called a reflection nebula. Now the reflection nebula, because it's scattering blue light, is actually going to appear blue. So you may see one nebular region, and there's examples of that in your book, where you'll see a nice red nebula, and then up in the corner you'll see a blue nebula, which is actually not from this nebula, although that gas is associated with it, but it's actually reflection from starlight that's actually passing or reflecting off of that other dust cloud. Another feature of emission nebulae are dark unionized regions within the nebula, which are called dust lanes. So you have these, this bright red thing, but you also have these dark dust lanes. These dust clouds have a beautiful, almost sculptured appearance to them. And there's one in particular where it looks like there's like 3 pillars of dark material against this lighter background. And at the very top of these things, you'll see, or at the edges, you'll see some areas that are much lighter in color. And on these edges, what's happening is a process called photoevaporation, where the material, atoms that are actually making up this, and also the dust particles, are actually evaporating away into space. So an example of this is the Messier object M16, and it's believed that maybe in another 100,000 years from now, that those structures will actually have completely evaporated. Okay, the next thing I want to talk about is a designation that's used by spectroscopists to describe an element's ionization state. So basically, what they do is they use Roman numerals after the symbol of the element. So the Roman numeral 1 indicates an atom that is completely non-ionized. A Roman numeral of 2 would indicate that it was singly ionized. The Roman numeral of 3 would indicate, for instance, double ionization. So, for instance, you could have H, which would be hydrogen, and then you could have like H1 or H2. You'd have these kinds of designations for non-ionized or ionized hydrogen atoms. Helium could have He1 or He2 or He3 if it's had lost all of its electrons. You'd have that kind of a designation. So these are just spectroscopic designations that you should be aware of, because they are mentioned in the textbook. If we look at emission nebulae, what we're actually seeing are H2 regions of space. That is places where the hydrogen is ionized in the emission nebula. If that weren't the case, we wouldn't be able to see them. We wouldn't have that red color. Now, analysis of nebular spectra. This is something that you would kind of anticipate just from what we know that stars like the sun are composed of, and even planets like Jupiter. This is kind of the composition of gaseous bodies. They're 90% hydrogen, 9% helium, and there's 1%, the remaining 1%, to be heavier elements. And the density, particle density, is on the order of 100 particles per cubic centimeter. So, again, that's still a very, very small amount of particles. Now, in the early part of the 20th century, astronomers and early spectroscopists looking out at some of these regions of space saw a greenish tint coming from some of these nebulae. And the greenish tint was very, very unusual, and it caused these scientists to think that they had found a new element, which they tentatively called nebulium. Now we now know, because this wasn't, at this particular time, the theoretical aspects of this really weren't well understood, but we now know that the green color is caused by a particular electronic transition of doubly ionized oxygen. So, and this is something that we don't see on Earth. So this would be an oxygen 3, doubly ionized oxygen. And we don't see that, we can't even produce this on Earth. And the reason for that is, well, let me try to explain this by an analogy for something that I use as a demonstration very, very frequently. Actually, I would do the demonstration for you, but I don't think, given the way things are in my little studio here, I don't believe you'd be able to see anything. So I think it would be more trouble than it's worth. But I can describe this to you. When I want to demonstrate something that looks like an aurora borealis to my students, what I'll do is I'll take a tube that is filled with air, and I'll use a Tesla coil, which generates a 50,000 volt spark, and I apply the spark on this tube. So I have a plastic tube that I can evacuate, and I've got a rubber stopper in one end of it, and the other end of it I have, which I'm using kind of as an electrode, is just a nail going through this. And I also have a hole in here, so I can pull a vacuum through here. Now, if I apply through the end of my nail, I've got the hole over here, and this is the nail. And if I apply at the end of the nail, the spark from the tip of the Tesla coil, spark will travel over to here. Anyway, so what you would normally see is a slight coronal discharge right at the tip of this nail. And that's due to the fact that we're actually exciting the nitrogen, the oxygen molecules that are in here. But it never really extends out any distance. It just goes to the very, very tip. Now the reason for that is that, yes, these molecules and the atoms in these molecules are being excited to a higher energy level. They're falling back down, or they would fall back down and emit light. But what happens is these excited atoms and molecules, there are so many of them that they actually wind up colliding with one another. And the collisions actually prevent, for the most part, any real excitation in this gas. So one of the ways that we can get around that is by pulling a reasonably good vacuum through the tube. And if I suck out as much gas as I possibly can, what actually winds up happening is that little coronal glow that's just right around the tip of the nail actually spreads out, and the entire tube will light up with a purple glow, which is actually due to electronic transitions, mostly of the nitrogen, probably some oxygen as well, that happen to provide energy of the photon is such that it appears violet to us. Now this green one, you never see it because in order to doubly ionize an oxygen atom, you would need to have virtually no other oxygen atoms around. And the fact is that, as I said before, the best vacuums, and my vacuum isn't nowhere near a really good vacuum, but the best vacuums that we have would only be able to pull a vacuum that's probably no more than 1/100th of a typical vacuum that you would see in interstellar space. So we can't really get down to the point where we can actually see this doubly ionized oxygen transition taking place. But nevertheless, you do see it, and it's been recorded in the emission spectra of regions of space. Our solar system, our sun, is in a very low density region of space, but it's hotter gases than what you see in the typical emission nebula. And our superheated, what's known as local bubble, as it's called, contains about 200,000 stars and was probably formed by a series of supernova explosions that might have actually occurred some 100,000 years ago or more. So that's not the formation of the sun itself, but it's just the collection of the stars into this local bubble. 99% of space contains no stars at all. So all the stars that we see, and there are very, very many of them. I think we said before the number was somewhere in the order of 10 to the 22nd stars, but 99% of space contains no stars at all. So most of it is a void. Well, you know, again, as I said, not a complete void, because we know that there are a few atoms scattered throughout all of space. And most of this void is at about 100 kelvins in temperature. There are also regions that contain dark dust clouds where the temperature is on the order of tens of kelvins, even lower than what you get in the rest of space. Much higher particle densities in these dust clouds. They're on the order of 10 to the 7th to 10 to the 12th, which would be a trillion atoms per cubic meter. Now notice I say atoms, not molecules, because at these low densities, molecules just don't form. Although they block out visible light, they still actually emit strongly at radio frequencies. So one of the reasons that we can actually, that we know anything about this is we can look at the radio frequencies that are observable. You know, we have radio telescopes, and we can actually, rather than looking at the visible light, we can look at what's happening at radio frequencies, which actually do get through. And one of the things that we see is the emission from these particular objects actually is coming from carbon monoxide, CO molecules. So we do have, in these regions, we do have a high enough concentration of atoms that we can form molecules, and the one molecule that is actually forming in there is carbon monoxide. Now there is a nebula, for instance, that's called the Horsehead Nebula, and if you actually looked at it, you would see it's literally in the shape of a horse's head, and this is near Orion, and it's an example of one of these dark dust clouds. You can also get spectroscopic information from absorption spectra of starlight that actually penetrates the clouds. So bands are sharp, enabling them to be distinguished from the star's own atmosphere, because you remember, if you've got a considerable concentration of atoms, then you're going to get band broadening. But with very, very few atoms, these things are going to be very, very sharp. Now, I was talking about before with carbon monoxide. This is sometimes referred to as 21 centimeter radiation, and this is, like I said, this is what we see from carbon monoxide, and there are other molecules that will actually emit this radiation at the in this 21 centimeter band. It's actually, I think it's 21.1 centimeters. So that's the wavelength of the radiation. It's and that turns out to be in the radio region of the spectrum. Now this comes from proton-electron, what's known as proton-electron spin coupling. And the way it works is this. There are two configurations that, and only two configurations, and we know this from those of you that have actually had chemistry and have looked at quantum numbers, know that there are only two ways that an electron can orient itself in a magnetic field. It's either going to be parallel or anti-parallel. So we look at, and I'm going to use the old Bohr model of an atom. So we've got a proton here, and we've got an electron here. The electron's orbiting the proton, but at the same time, the electron is also spinning on its axis, as is the proton. So let's say the proton is spinning in this direction. Now the electron can spin with respect to the proton. It can spin in one of two ways. It can either spin parallel to the direction that the proton is spinning. So we've got both of them going, as I've drawn it, counterclockwise. Or the other possibility is that the proton is spinning in this direction, spinning counterclockwise, and the electron is actually spinning clockwise direction. Now, the lower energy level, and nature always has a tendency to want to seek the lowest energy level. It's the most stable level that you can get to, the lower energy level. So this thing now is spinning in the opposite direction. There's enough energy at the temperature where this is occurring to actually promote electrons from this anti-parallel spin configuration to a parallel spin. So this is increasing energy this way. Energy's going up. To the parallel spin, you know, let's say we're at 100 Kelvin. There's certainly enough energy. This turns out to be a very, very low. This is not something like we've seen some electronic transitions might require heating things to thousands of kelvins in order to get them to take place. But this is something that happens very low, maybe in the tens of Kelvin or 10 Kelvin region of space. So these kinds of transitions are taking place all the time. So this is the parallel spin state. What's happening now is that once this is up here, it can fall back down to the ground state. So when it does that, it emits a photon. Now these are not visible photons because they're very, very low energy photons. So the photon that is actually emitted now is going to be a very, very low energy photon, which is going to happen to come out in the 21.1 centimeter region, which is radio frequency. So even though we can't see this thing in the conventional sense, that there's no visible light being produced, there's still this 21 centimeter radiation, which we can pick up with a radio telescope, and that enables us to be able to look at these things and really determine what's going on. So that's kind of an interesting thing. And the exact position of these peaks actually varies. It's not always centered exactly on 21.1 centimeters because of galactic motion relative to the Earth. So we're looking out in the galaxy. It's moving, or a distant galaxy, and it's moving relative to the Earth, which means we're going to see potential red or blue shifts depending on the direction that it's moving relative to the Earth. And that's going to cause slight shifts in this 21 centimeter band. But we call it 21 centimeter. It's going to be somewhere around there. And as I said, at around 100 Kelvin, there's certainly enough, 100 kelvins, there's enough energy to cause this excitation. Now, in very cold regions of space, somewhere around maybe 20 kelvins, you can actually get concentrations of particles as high as 10 to the 12th particles per cubic meter. And when you have that many particles, then they can combine to form molecules. And these can also be detected by radio emission. So not only carbon monoxide, but there's a whole host of things. There's a couple hundred, I think, at this particular point in time that have actually been discovered. And some of the things are unusual, and more common things that we see are, in addition to carbon monoxide, are things like hydrogen cyanide or hydrocyanic acid, hydrogen, a carbon, and a nitrogen, highly toxic gas. We also have ammonia. We've seen that, though, in the atmospheres of some of the Jovian planets and moons. Water, methanol, methyl alcohol. This compound, CH3NH2, is methylamine. These are all listed in your book. Ethanol, which is unusual, ethyl alcohol. So that's CH3, CH2OH. This is what you'd find in the little schnapps, but there's certainly not enough of it for you to, in these regions of space, for us to worry about. Aldehyde, which is this, and formic acid, which is this. These are things that are listed in your book. Sometime in the 90s, although it's still not been confirmed, so it may not, someone has claimed, and I haven't really investigated this, until we get confirmation. I'm just going to mention it, but there's no certainty of this. This is an alpha amino acid. This is amino acetic acid, also known as glycine. Now, people will be pretty excited about this because glycine, after all, is a biological type of molecule. It's it's an essential amino acid. So people that are looking for the possibility that life might have somehow originated in the cosmos through the formation of molecules like that would like to see something like glycine. Of course, that doesn't really prove anything at all, but it's interesting that it might be out there. Other things that are not listed in your textbook that also have been found are things like benzene, which is actually 6 carbon atoms. There's a carbon atom at each point here. It's a cyclic structure, and there's hydrogens at each point along here, and naphthalene, which actually is 2 of these rings fused together. And then you can fuse more rings together, and you form what are referred to as PAHs. And these are polynuclear aromatic hydrocarbons. Both naphthalene and benzene and other compounds like this are referred to as aromatic hydrocarbons. And polyaromatic means just that there are more than one ring. Well, probably more than 2 rings even. But you could call the naphthalene could still fall into this this category. And again, and the other thing that people have found is that sometimes these things will even be functionalized. That is, they'll be like this group that's with a carbon, 2 oxygens, and a hydrogen, which is called a carboxylic acid. You'll find these things with carboxylic acids on them. So these are interesting because they're more complex molecules. And these things have actually been found on this Murchison meteorite that was found in the I guess it was in the Antarctic, which they believe is possibly of Martian origin, and so they're finding the same kinds of molecules present on that meteorite. This is something, if you're looking for evidence of life on other planets, finding stuff like that, gets you kind of excited. Other things that we find in there are, in addition to that, are ethers, such as dimethyl ether, which is CH3, oxygen, and then another CH3. That's dimethyl ether, that's been found. Methyl mercaptan, CH3SH, the sulfur analog of methanol, methyl alcohol. Acetic acid, this compound where it's, rather than having the amino group on there, the NH2, you just have another hydrogen, CH3, CO2H. It's acetic acid. Those of you that have had chemistry probably know this already. Another molecule is acetone, which is CH3. I don't expect you to know all these structures, but I would like you to realize just what the diversity of some of these molecules happens to be. And this group here, the C double bond O, is called a carbonyl group. And then you have another CH3, so that's acetone. Acetaldehyde, which is CH3COH, has also been found. And then there are a lot of ionized species and a couple of things that I couldn't even assign a structure to because, at least not any stable structure. In the one paper that I was looking at, these things were described as molecules, but there's no way that you can write a stable structure. So I assume that they're either what we call radicals or ions of some sort.